All set.
All set.
Terrific. Well, welcome everyone. And I'm really excited to be here with you and talking about quantum optimization and sharing some real world customer success stories. During today's webinar, I'm going to be really trying to help you understand why optimization is a core capability for quantum computing, how it's differentiated from classical computing, and then we're going to walk through some customer success stories and places where customers have seen advantage in incorporating quantum technology in their business applications involving optimization. And then I'm going to talk about the technology platform that's basically supporting all of this. And then we're actually going to take a look. We'll run a demo, and I'll show you some of the resources that are available online. So I think always the place to begin when we're talking about quantum computing is what is a quantum computer? So here's a handy photograph and summary of our DWave Advantage system. What I want to describe here is that a quantum computer uses quantum effects to accelerate calculations. And that means that quantum effects are a resource for the computer, for it to use to help with those calculations. Now, quantum computers can use quantum effects in different ways, and that has led to different models of quantum computing. There's the gate model targeting quantum chemistry, and there's the annealing model, which is targeting optimization. So we're really going to be talking about the annealing model here. And the principal reason is because when you start adding the controls into a gate model system to allow it to do quantum chemistry, that actually introduces overhead that makes it difficult to apply to optimization. Whereas in annealing, it's purpose-built to work on optimization problems, which is also relevant to the optimization functions that are used in advanced analytic techniques and artificial intelligence as well. So, basically the quantum effects, when you're working on an optimization problem, you may have a particular solution in hand, and the computer stores that information, and then you want to move from that solution to a better solution, and then continue improving, moving from solution to a solution, improving over time. Quantum effects helps the computer to move between those solutions more quickly. The way I like to connect this to our everyday life is, let's say you're playing a card game. Maybe you're playing bridge, or you're playing with your kids, you're playing Pokemon or something like that. You've got a handful of cards, and what's important is the combination of cards that you're working with. Maybe the hand that you were dealt, you're not super happy with, and so you want to exchange cards with the deck. A classical computer is stuck in this problem of having to change the cards out one at a time. So you take a card out of your hand and discard it, and then grab a new card from the deck, and then look at the overall improvement, and you continue doing that. But each time you're doing that, you're letting go of one card at a time, and that's not a very effective strategy. And it's not an effective strategy because, particularly when you're working on large optimization problems, there's so many different combinations of changes that you can make. And so the quantum computer is allowing you to basically, pick out multiple cards from your hand, and then actually search the deck and grab a new combination of those cards. So it's sort of like one of those power moves in a game. I'm sure everyone's played a game where you're allowed to basically exchange and do like a non-local update. You're not just moving one card, you're actually exchanging a whole set so that you get a much stronger working set in your hand. That's the kind of coordinated move that quantum effects enable, that allows quantum computers to really accelerate computations and optimization. Now, what do I mean by accelerating optimization with quantum effects? So if you're in the space of industrial optimization solving, there are a few strategies available to you. And where things get difficult for a classical computing technology is when you're not just optimizing flows of things, like, level settings, like, how much am I going to turn the power up on this electricity transmission line, but rather you're trying to take into account effects, much like I was saying with taking a card out of your hand and putting it back in, assigning a resource to a particular problem. Those types of things make it difficult for classical computing. And in those difficult problems, some of the strategies that a classical computer might ordinarily use, like, looking for the steepest downhill slope and then using that slope to give it some sense of direction and how to make a move through the solution space, they're not available to classical computers anymore. So really the smaller set of strategies they have available is to either try to reduce the problem to make it smaller, or to study the problem and detect some sort of structure that allows it to make big moves in the space. But one thing that no classical algorithm is able to do is increase the dynamics, the speed with which it's able to move between solutions, And that's because all classical algorithms and industrial optimization solvers are running on the same hardware. And that hardware is fixed and limited by classical physics in terms of how quickly it can dynamically switch between solutions. And what we were able to publish in Nature is that, in fact, quantum effects have now been proven both theoretically and with experiment to accelerate these moves, these dynamics, and these hard optimization problems. And this graph on the right showing these blue, teal, and orange curves show that quantum annealing actually have a steeper slope of descent as they're improving the solution quality in a minimization problem. And this is not possible with classical computing. So all of the improvements we've ever had with classical computers don't show this level of speed up, which is actually scaling. So the advantage is increasing as the problem sizes increase. So there's so many strong motivations here for using quantum computing technology hybridized with classical computing technology to address really difficult optimization problems. So let's talk about the fact that, at DWave, we're really trying to pivot the entire industry so that we're not talking about experimentation anymore. We're talking about the operational use of quantum computing technology to bring value to business. In order to do that, we can't be talking about toy problems. These are not sort of 12 variable problems or something very small. It needs to be at enterprise scale, because that's the point at which these problems get very difficult. That's the limiting level. And while in quantum computing, there is a roadmap of applications that are going to be emerging. And some of them have potential impact in the future, but we're really talking about quantifiable return on investment today, applications that you can run right now and get business value. And we're leading the way to help businesses transform and become more effective in their operations. How does that materialize? Well, in terms of the actual business impact, it usually manifests in a solution that accelerates a business's speed to decision. So they're able to make decisions in complicated situations much more quickly. It can also be about increasing effectiveness. So, if you consider, let's say, I'm using the word effectiveness very deliberately here. If you consider, let's say, the flow of material through a port, increasing efficiency might be about maximizing the flow of the material. But in order to be effective in real-world scenarios, you have to be able to maximize that flow in a context where you have unexpected events or changes in plans. So you have to be able to adapt and adjust. And that's really about driving resilience and agility. So the ability to replan quickly, to be able to consider new scenarios as they're emerging and allow you to adjust. Because while you may have the interest and the support in your organization to be agile and to be flexible, you also need the technological resources to allow you to replan in those complex scenarios and get effective operational either configurations or plans for how you're going to run so that you can execute effectively. All right, so let's look at some of these customer success stories of quantum in action. Now, I have talked to a number of folks in applications and supply chain optimization. One great example would be Hermes Germany that we're working with our partner, Quantum Basel. They're exploring vehicle route optimization in a scenario where they have 50 depots and 17,000 parcel shops, and they want to really look at how do they coordinate the movement of all of the trucks who are passing and circulating between the parcel shops and the depots. They want to be able to better optimize these routes in terms of time and distance, and that provides an advantage to the organization in terms of more effective operation and reduced costs. But it also allows them to achieve some I think, larger societal goals like reducing CO2 emissions and really getting these important supply chain applications running in a much more efficient way. So that includes applications like final mile delivery, and I'm going to conclude today's webinar by actually giving a demonstration of like a multi-vehicle routing type of demonstration. It also includes like warehouse optimization, both the placement of warehouses to maximize flow within a particular region, or the placement of material within the warehouse in order to maximize the operations of that warehouse, and also like the general application of logistics routing. Pattison Food Group is a great example of optimization put into application. So they started with one of their grocery store chains, and now they're looking at expanding that across all 13 grocery brands that they have at Pattison Food Group. During the pandemic, at-home grocery delivery driver scheduling became a very important application. And they were able to build an application that reduced the time taken to build those schedules by 80%. That's a very significant savings. So they took that application into production, and it's been running since October 2022. So we are living in an age where quantum computing applications are in production and being run right now, so that when I order groceries from Save On Foods, the delivery drivers who are bringing them to my house or to work here at DWave, their schedules have been quantum optimized for quite some time now. The outcome of this is that they've started looking at other scheduling applications within their business, including in-store auto scheduling. So this is a challenging problem for many businesses because at their locations, they actually have multiple departments. And so their workforce is trained to work in some of the departments, but not across all of them. And that means that as they're creating these schedules, they're looking at, okay, what is our demand expected to be this week, each day of the week? And then, how is this week different from the other days of the year? And then we also want to make sure that this is a really employee-centric schedule so that everyone's getting, full work weeks, ideally suited to their preferences. And that introduces a lot of constraints in terms of how the scheduling is produced. That application they've now built, it's operating across dozens of stores, I think up to 100 stores now. And Lindsay Dukowski came and presented at our Qubits user group conference, talking and sharing with our other customers that their workforce is expecting to save 50,000 hours annually with that application as they're rolling it out. So we're talking about really significant impacts in terms of optimization improvement across businesses. Now, another example, which I think really speaks to people, is the optimization of the movement of cargo around the Port of Los Angeles. This was built by Savantex, an independent software vendor working with the port, and really showcases a challenge, which is that the real estate of Pier 300, the busiest pier at the port, is not getting any larger. They're not going to get any more space, but supply chains are growing, and they need to be able to have more capacity to flow material through that pier. And so Savantex helped to build a solution which allowed them to increase the amount of cargo that they were handling by 60% each day, while also simultaneously reducing the truck turnaround time by 12%. Huge impact here at scale when we're talking about systems. And what makes these problems challenging is that the cargo is stacked in the yard, very much like cards when you're playing solitaire. You have to take the top cards off before you can get the cards below. And each of the choices that you make affects the sequence of cards or the sequence of containers rather, that you can then move. So they were actually re-optimizing at each of these stages so that based on the real conditions of not just when were the trucks scheduled to arrive, but which trucks were actually available at each given moment, so that they could call our system every 15 seconds, 2 shifts a day, 6 days a week to re-optimize that sequence based on real conditions. Now, transitioning here to electric grid optimization and energy grid optimization. This is a fantastic example because in its traditional form, it's very well suited to classical computing. In a standard model of an energy grid where you have a power plant, which is producing power in one location, and then it's radiating out that power in sort of a hub and spoke model. So all the transmission lines are moving away from the power plant. That's an optimization where you're, in time, varying the amount of power flow down the transmission lines. And the transmission lines that are going to the east don't affect the power transmission levels that you might want to optimize for the west. So the decisions you're making are continuously variable. You're constantly adjusting levels. So calculating gradients is available to you, and that's a big advantage for classical computing. And the second thing is that independence of the decisions that you're making, that's also a big advantage for classical computing. But what's happening with energy grids is that they're modernizing. We're moving from a hub and spoke model with major power plants to a scenario where power is being produced in multiple areas of the grid. And that's very powerful as we're moving towards sustainability and more, diverse sources of energy like solar cells, which are only producing energy some of the time. And that means that the energy grid has to be, drawing power from some locations at some times and then transmitting power to those locations at other times. And that switch is a binary effect. That's a choice that's either, power is flowing in or power is flowing out. And because they're happening in diverse locations throughout the grid, that means that each of the decisions you make about where power is flowing affect other decisions in the grid. And that's also getting complicated by the fact that we now have more diverse energy storage. I've read articles about providers looking at using the fact that we have, cars with very large battery arrays that are charging at night, but they could actually draw from those cars at some times if it was more energy efficient to do so. In order to be able to move into that energy grid of the future and achieve our more effective energy use, in a more sustainable way, which I think everybody, wants to be able to move to, that's going to be held up. It's going to be slowed down by the complexity of how to optimize that network. And the Applied Science University in the Netherlands, TNO, looked at how to do those calculations on our quantum computers and actually found that they were able to study, the electric energy grid in Germany and partition it more effectively using our quantum hybrid techniques than they could with classical solvers. So really highlighting, I think, for this industry, how, quantum hybrid technology, incorporating quantum computers and classical computers and what they each do best is actually going to be the solution that allows us to operate these systems more effectively. And if we can operate them more effectively, that means we can roll them out more quickly, which everyone wants to see. Lastly, I'm going to bring up an example in financial optimization. So this is specifically with CaixaBank, where they were looking at portfolio optimization hedging and bond portfolio optimization. Now, quantitative finance is an interesting example because it's one where it's very difficult when the organization is facing am I going to build this solution myself, or am I going to buy this solution from somebody else? A lot of banks compete very strongly with one another based on their algorithms and their signals. So they're very reluctant to share information with outside firms. And that's why, in this case, it was very helpful that their team was actually able to build this solution themselves with support from our technical advisory group. And they had a set of calculations that they were already doing in their business, and they were able to match the quality of those calculations, but reduce the time to solution by 90%. So a significant gain here, and I think a very strong signal from a Spanish bank looking at their real data, which is really difficult for firms who are not in the quantitative finance space to match or to provide those demonstrations. Okay, so that takes us through a set of customer success stories looking at quantum optimization, not just in terms of what its potential is, but in terms of actually putting it into application, incorporating in that workflow, and seeing its contribution in those business contexts and in those applications. So when I have been out speaking, people have asked me, what is the most significant thing that's happened in quantum computing in the last year? And this is the result I share with them, which is that we have demonstrated a calculation in 20 minutes that would take 1 million years to do on a classical computer. And that means we've really entered the time where quantum computers have the ability to calculate things that classical computers do not. So what we have done here is working with researchers that around the world from 11 different organizations. We were able to use a lot of time on the Frontier and Summit supercomputers at Oak Ridge National Labs. Frontier is the most powerful supercomputer in the world today. And we were able to do some very intensive calculations on these quantum material studies. So the reason for the motivation of these quantum materials is threefold. One is that we know that they're very difficult. They've been well studied before. So we actually know how much work has gone into studying them. We know what their properties need to be. And in addition to that, we have strong theoretical foundations to understand how that difficulty scales as the problem sizes get larger. So when we do calculations at small scale, we can get accurate information about how much work that is going to be, how much that effort grows with time. And that's how we're able to get these results, where we're able to showcase these timescales, which are really inaccessible by any other means. The other important element to this is that our DWave quantum processors, the first generation of our processors, consumed 15 kilowatts of power. that power level at an industrial scale is relatively low. It's the kind of thing you might use in a few offices in an office building or something like that. And what's interesting is that that was our first generation quantum processor. Our fifth generation commercial quantum processors that are online right now, they also consume 15 kilowatts of power. So while we've seen this dramatic improvement in performance and these huge performance gains, there's no power growth across those 5 generations. And the reason for that is because the actual quantum processors themselves, the circuits are printed in metals that when at their operating temperature, they don't produce any resistivity whatsoever. Now, I know that sounds like science fiction. It sounds like amazing. It's fantastic physics. And it can be used in this processor technology in such a way that the quantum processor itself consumes less than a millionth of a watt. And that means that if we can take some of these important calculations and offload them from classical computers onto quantum computers, we can, dramatically change the performance profile of those applications. So, here's where the significance of these quantum materials studies comes in, is that the mathematics that underpins these studies is the same mathematics that's used in heuristics for industrial optimization solvers. So this has similar applicability to and relevance to optimization. And it's also very similar to neural networks. As a matter of fact, John Hopfield and Geoffrey Hinton, who just won the Nobel Prize in Physics for their work in neural networks and the way that they behave, the Hopfield network is actually the same as the architecture of our annealing quantum processors. And the bipartite graph is this purple graph on the top left here, that we chose that lattice structure as one of the structures studied precisely because it has relevance to neural networks and specifically quantum neural networks. So some very exciting work here with a lot of potential for being able to take workloads that are very difficult for classical computers and are consuming a lot of power in that space and really offsetting that in a low power context with quantum computing. So how are we supporting this with our technology stack? Well, DWave is known as a full stack quantum computing provider. So we have manufactured and produced 5 generations of commercial annealing quantum computers. And the largest, most highly connected quantum computers on the planet right now are annealing quantum computers with 5,000 qubits and 15-way connectivity. And that's connectivity is increasing to 20-way interconnectivity, as you can see in our Advantage2 prototypes, which are online right now. That's a good point to mention, like they're online and available to you in our Leap Quantum Cloud service. So this allows you to sign in, get access to the systems, monitor your usage, look at open source examples for applications, and then build off of those open source examples to get applications built quickly. We have greater than 99% uptime with real-time access to those systems. So really the kind of service that people expect. And we've now released service level agreements for our contracts with our customers, which is what they expect for their production applications running on that cloud platform. We're trying to make it as easy as possible to use this technology with our Ocean developer tools. The name of the game in quantum computing is quantum computing is going to be won or lost based on ease of use, right? And because we're working on quantum computing, we're tremendously focused on that. So our open source tools available on GitHub are really trying to make possible for a small team of 2 to 3 developers to build really high value features in business applications. And those can be programmed in Python. And because they're open source, you can work at the application level, but you can also dive down through the technology stack all the way into the quantum machine instructions themselves. And we have a launch program with our professional services team to help our customers along their journey, wherever they might be, whether it's from problem discovery, looking at, okay, what are the applications in our businesses where quantum computing is going to be able to, provide value, and where, there are direct relevance between quantum computers and our applications, all the way up through, building proof of concepts that get you business information about the return on investment you can get from running those applications, through, phased pilot launch programs and full production releases of those applications. Our network of commercial scale quantum processors as worldwide in Leap. We've got systems in Burnaby, Canada, our commercial scale quantum processors, as well as our Advantage2 prototype. In Los Angeles, California, we have a system at the University of Southern California and the Information Sciences Institute that's there. In Jülich, Germany, we have a system at the Jülich Supercomputing Center. And we've announced that we're going to be installing a system with Davidson Technologies in Huntsville, Alabama. So that's going to be upcoming. So really, we're talking about a worldwide network of quantum computing systems on which these applications can be built. And, in order to build these applications, we're really pushing for high uptime, trying to be as high performant as possible. So that, we're talking about, 3 nines and, looking at aggregated API uptime of, potentially as high as 4 nines, in terms of making sure that when you're using this quantum computing technology, you're getting quick responses and that your systems are available 24 hours a day around the planet to make sure that they're operating effectively. A really important innovation that has made these commercial scale applications possible is hybrid solvers. It's about recognizing that quantum computers are about accelerating some problems, some instances of problems, and classical computers have some very valuable heuristics that they can contribute to problem solving. And at DWave, we've studied both quantum and classical systems for so long now that we know exactly how to fit them together, and we're continuing to improve those methods for combining them consistently over time. By putting them together in hybrid solvers, we're really enabling you to do much more rapid application development. It's allowing you to reach applications at full scale, full enterprise scale. And as our technology improves, whether it's new releases of quantum computing generations themselves, or the algorithms that we're developing in these hybrid contexts, all of those continuous improvements get drawn into the full stack and create a compounding benefit for the applications that are running on it. So this, I think, has been really critical. And really, it's a scenario where, no quantum computer is ever going to be used solo in an application, because whatever problem that it can solve, there's always going to be complementary algorithms that can run around it to allow us to reach that larger scale. So hybrid quantum classical techniques are the way that quantum computers are going to reach their commercial audience and bring businesses value. So, I talked about this journey, and, I think have a look at this slide and consider, where are you on this journey? Are you at a point in your business where you're exploring, you're trying to discover the places where quantum computing can add value so that you can help share with your business how they should begin incorporating it and preparing? That's the early stage, and we can really work with you to help you identify which are the places where quantum computing can provide value in the shortest timeframes, and the order of like weeks or months. We can also work with you to help accelerate. If you've got an application like many of our customers do that can bring you millions of dollars of value every year, we can help you accelerate that development of a proof of concept so you can demonstrate to your business the return on investment that can be achieved by running these quantum applications. And then support you through the change management process of going to pilot, production, release, and through on a journey towards full production operation. And we've been through this with a few organizations as they're going through this journey, and in many cases moving to multiple applications, which is a really exciting milestone in the development of quantum computers. Okay, with that, I'm going to switch screens to a demo. While I'm switching screens, I'm just going to flash up this slide to a set of related resources so that you can look to them and pull up more information. So I'm going to share my browser window. All right, I'm looking for a thumbs up that's showing well. Susan will come on if something's a problem. All right, so if you want to have a look at our Leap Quantum Cloud platform, not Nintendo, I use that for checking my network connection. Just search DWave Leap, and any of the top hits that come up are basically going to help take you to this location. In this case, it's cloud.dwavesys.com. I've already clicked on those links and I've signed into our system. And so this is the Leap dashboard that shows up as you're using the system, showing your usage and the problems that you've been submitting, as well as the solvers that are available to you. So our commercial scale advantage system, which is in Jülich, Germany, is available on EU Central 1. And then in North America, the systems that are in Los Angeles and then also in Vancouver, as well as the suite of hybrid solvers that are available to you. Now, certainly, as I've been talking with folks and developers, it's not really the case that people start building software from a blank page. They're really starting from an existing example. So we've created a number of examples to look at production scheduling, logistics routing, decoding cell phone signals, a whole variety here, so that you can begin with these, learn about the technology, but then start adapting them and customizing it for your business applications so that you can share with your colleagues where the applicability is and how quantum computing can contribute there. I've opened one of these examples, which is our multi-vehicle routing problem. And in addition to, when you're opening one of these examples, you can view the code for the example on GitHub. But what's great is that GitHub has code spaces now, so you can actually open a developer environment direct in your browser. So we have set this up so that the containers are already available with all of the system settings, the code pre-installed, so that really your environment, you can get up to productivity in minutes. So I have actually done that here. Here's the README for the application, which initially pops up, but all the coding files are here, so you can begin looking through the code and how that's written for the call back and forth. And then once you actually start running the application, which I've already started in the terminal here, this is turning these temporary resources into a server. So very much this demonstration is not just a demonstration of calling a quantum computer to solve an application. This is like the miniature deployment of the web application itself, where these temporary resources are now a server. They've opened up a port to a web application GUI front end, which, fingers crossed here, is not timed out since I started this, but if that's the case, we'll reload it. So this actually shows, a vehicle routing problem in the city of Rockhampton, Australia, where you have a depot and then a variety of different deliveries that you need to make. Now, if this was just a single vehicle, this would be a traveling salesman problem, which, although it's in the class of very difficult problems, when it's limited to the surface of the Earth, classical computers can actually provide good quality solutions at large scale. The difficulty comes in when you start incorporating other industrial constraints, particularly a scenario where you've got a number of vehicles to deploy. So here I'm talking about 6 vehicles. So there's really a segmentation where you're making resource assignment problems in addition to routing problems. So we're looking at 6 vehicles across 70 locations. So we're going to pass this to our hybrid solver and give it 10 seconds to run the problem. Now, the UI itself takes a little bit of time to load, so this may take anywhere from 15 seconds to 25 seconds as I'm running it. But what I've just done by clicking there is this web application is called a server. It has sent this instance to our hybrid solvers in the cloud. That's deploying classical computers, ingesting the whole problem, working across it, and then submitting problems to our quantum computers underneath. And then as the quantum computers suggest moves through the solution space, it's incorporating that into the larger problem. So there we are. We have a complete solution from the system here, showing the routes for these different locations, color-coded by the routes for the 6 different vehicles. And it allows us to look at them in this results page, where we can look at each of the individual vehicles and the distance traveled and the locations that they're running. Now, in addition to this, I can also go back to this map and I can select a classical approach to solving this problem. Now, I'm going to run this classical approach, and I want to make a cautionary statement here, which is that this is not the level at which we would do benchmarking. This is a small-scale problem, and these problems get difficult at large scale, particularly when you're considering, business constraints. But it allows us to make some qualitative comparisons that we typically see based on the difference in approach between, quantum and classical, where classical techniques are very good at looking at local updates, and the quantum computers are helping to make larger updates in the solution space. And also considering comparisons between, the work and the assignments between drivers. The net result is that, okay, we're looking at the distance traveled, and we've got a significant reduction in distance, which is going to translate to, less cost with the quantum hybrid solution and, less CO2 emissions. But we can also end up in these scenarios on the classical side, like this one we have here, where driver 5 and 6 are doing similar numbers of deliveries, but one of them is driving 3 times as much distance. When it comes to practically implementing optimization solution, there's more than the technical element. There's the human element to it. And this really conflicts with that sense of justice and fairness that a lot of people have. And that's often what prevents businesses from being able to leverage these technological advantages. And in order to take into consideration, okay, where is the work? How do I balance the work? and get it more evenly balanced across my workforce, you have to consider these nonlinear relationships, which are very difficult for classical computers to work with. And so many times when we're working with our customers, it's the evenness of the workflow, which is an important element for them, where we can provide value. And that actually helps them with getting the problems adopted by their workforce. In fact, many of our customers have talked about the fact that once they've shown what these solutions are to their customers, to their employees rather, they're actually asking them to roll it out more quickly. Now, the last thing I want to show you is a resource online in our documentation, where in our problem-solving handbook, our talented documentation team has built a workflow for developing quantum applications. So this follows through the process from discovery through to testing and iterating that we use and that we have found is very helpful for building applications. And it includes these resources here about the characteristics of candidate problems. So if I expand this section here, you'll actually see that there's some really sort of real world description of, you're looking for applications in your business where there are some decisions that you need to make that might be binary. So in scheduling, did a task meet its deadline? Yes or no? Did the crew make its flight? In networks, it would be, did this network node experience a failure or not? And in finance, it's like, okay, well, did this loan go into default? It also is valuable to look at decisions where it's integer variables. So like, how many of these boxes can I get loaded onto this truck, right? That's an integer number. It's not going to be, 0.17 of a box, that I can add to this truck. And it could also be categorical problems. So like, is something part of a set? Like which shift should this particular employee work? Or, if I'm doing map coloring, what color should I choose for this segment of the map? Is it red, blue, green, or yellow? What team should this individual be on? So in addition to these kinds of decisions, which take, are part of these optimization problems, you also have these quadratic interactions. So individual decisions affect other things in the network, like, a missed deadline starts affecting other tasks. And if you want to prevent gaps between consecutive machine usage, that will help you save costs. So you want to consider those network effects. If you have a failed network node, that can change the load on other nodes in the network. If you've got, a defaulted loan, that can basically affect the risk to other loans. So those kinds of network effects, those sort of like knock-on effects that you can get in networks and that affect your resource pool, those are the kinds of things that make these problems really difficult to solve. So have a look at this resource, and the rest of our documentation is fantastic, and it's a great way to get started and to accelerate you on your journey. And with that, let me pause and we'll go to Q&A.
Great. Thank you, Murray. We have a lot of really great questions that come in, some of which you may have answered as we went on, but I'll ask them anyway.
Okay.
First question, how complicated is it to turn optimization problems into equations you can use, and who owns the IP?
So that's a great question. It's certainly, if you have a math or optimization background, that's the kind of thing that people do all the time. When I'm talking to people who work in artificial intelligence or in quantitative finance, that is also a programming model that they use every day. But if it's a skill that you want to pick up, it's actually quite straightforward. And in fact, we have our learn.dwavesys.com, where we have like a professional programming course to help teach you those skills. And in our examples, it shows you sort of like, here are the parameters, here's how the equations fit to the particular objective you're trying to optimize, and then there's sections in the code that describe that. Have a look at the bin packing example as a great place where that's really described in the README. To your question about the intellectual property, when we're working in our launch program, helping our customers, when we're building the application, that application code becomes yours. So we may build it for our customers using our open source tools, but then we're providing them with that application for them to run. And our intellectual property is behind the solver API.
Okay. On a different tack entirely, the term Spinglass has no meaning in a presentation to a board of directors. Is there a more BOD-friendly explanation?
Yeah, I think so. I mean, I try to avoid the term Spinglass. It's meant to indicate a class of difficult problems. However, it's effectively saying optimization problems, or a set of problems where you have a set of binary decisions that you need to make that have this network, and this knock-on effect on one another. So typically, I mean, I think a much more relatable example would be to say that like the core machine instruction for an annealing quantum computer is very much like a quantum neural network. And it's the type of neural network that John Hopfield and Geoffrey Hinton have studied, those two Nobel Prize winners who just won the Nobel Prize for Physics this year. And that sort of quantum neural network has applicability to optimization problems and industrial optimization as a heuristic used in combination with classical computing heuristics. So if I'm talking at a board of directors level, I would focus on quantum optimization, and I would focus on these customer success stories and the businesses using it, and only start diving into that lower level of detail as asked. But I think the quantum neural network is maybe a little bit more relatable in today's society where, so many people are talking about artificial intelligence.
Okay, can your system be used to reduce carbon footprint in data centers? I understand they use a ton of energy to run a data center, so could you save them energy by computing more efficiently?
I think that there's two ways to look at this. One is that if there are applications running on the data centers which are, quite inefficient, so they're consuming a lot of the resources in the data center, but it's in one of these optimization spaces where that can be translated into a quantum hybrid solver, which is able to get solutions in less time. That provides a direct savings, that CaixaBank example of, getting the same result in 90% less time. That means that you're getting more problems through that system for the amount of time that it's consuming energy. But I've also talked to experts in high-performance computing who talk about the scheduling and distribution of workloads across nodes in the cluster. So a high-performance computing data center is actually a whole bunch of, computer processes and chips that are distributed. So that means the work needs to be distributed through them. And that resource assignment problem is actually about, which chunk of work is going to go to which resource. So I think that's an exciting application that could look at the more effective and efficient use of data center resources.
Okay. Are there scenarios where quantum computing would optimize AI training?
Yeah, absolutely. There are a host of ways to consider using quantum computers in AI applications. We have some that are very readily available and easy to use to do with feature selection. So if I go back to these code examples and search for feature selection, there's an example that you can look at right here. We've got a scikit-learn plugin, which allows you to basically incorporate this. So if you're building predictive machine learning models, which incorporate feature selection as part of that workflow, you can immediately quantum hybridize it very quickly. So that's from like the relatively turnkey for folks who are, building their own machine learning models. And then for those who are really looking at like what are like some of the open questions and research questions associated with quantum computing, a lot of people are looking at our systems to draw statistical models for restricted Boltzmann machines and discrete variational autoencoders or other discrete models within transformer models. So I think there's some great capabilities you can start using right away, and there's also some fantastic emerging capabilities that can really engage the machine learning and artificial intelligence research communities right now.
Okay, thanks for a great talk, Murray. I'm very much interested in solving hard combinatorial problems with a few hundreds of binary variables, and we've been having some success on DWave hardware so far. But for some reason, we can't get our quantum algorithm to scale up to more than 80 binary variables. Any insight on why this is the case? For example, if we were able to solve a problem with 300 plus variables, we would be able to solve a famous open problem in combinatorics.
Okay, so that's a great question. One of the things is, the place I would begin when I'm talking with folks is that, absolutely have a look at direct quantum programming. But also, if you're trying to build applications, look to our hybrid solvers so that you're not necessarily having to constrain it to the structure of our quantum machine instructions itself. That actually allows you to consider like a wider number of variables beyond binary to like integers and even continuous, and it makes application development much faster. I'd love to see that application scaled up to 300 variables, and we have a technical advising team that actually is very talented in helping people identify, okay, how to scale up their problems, or what are some of the tips and tricks that we've tried to help them get there. And if you're interested as well, they can connect you into our launch team, who can actually look at the problem and work with you on the formulation and try to see if they can help unlock some of those roadblocks for you.
Okay, we had some questions regarding energy consumption and cooling. So someone is asking 15 kilowatts over what time period?
So 15 kilowatts is in power. So that's energy per unit time. When our systems are, like if our systems are online 24 hours a day, 365 days per year, that means 15 kilowatts for the entire year. In the same way that modern data centers are now using multiple megawatts of power. So they're using millions of watts all day long, 365 days of the year. So that's probably the way to think about it. If you're going to turn it from power into energy, then you would multiply it by the number of hours, or the number of seconds, I guess, using SI units, and then you'll get it in units of joules. But I typically use kilowatts as a comparison because people are often using megawatts as a sense of the power consumption in data centers.
And a related question, do your energy consumption numbers include cooling costs? What temperatures are required to run the DWave system, and what are the related costs and technical challenges?
Yes, they absolutely do include cooling costs. In fact, that is the cooling cost. Our laptops and in our data centers, I mean, they have cooling systems. They've got fans, they've got water cooling as well. And that's to maintain operating temperatures at room temperature. It's a room temperature operation in data centers, which is helpful. But then when you turn them on, they heat up. So you have to basically get the temperature down to room temperature. In a quantum computer, your energy consumption goes into dropping it down to low temperatures to operate. But the great thing is that once you're down to that low temperature, when you turn on the quantum processor and get it to work for you, it's not producing any heat there. So you're not trying to draw heat away from it because it's only producing, a millionth of a watt of power consumption, which is incredibly low. So in fact, the pumps and compressors and the refrigeration systems themselves are all of that cost. So that's a great question, an interesting breakdown in terms of the power consumption there. Any other questions, Susan? Oh, you're on mute.
Sorry, I was on mute. Can you please mention the research publications that prove that quantum annealing optimization solutions have greater dynamism? Could you also please explain why higher dynamism is desirable?
Yes. Okay, so let me go back, share my other screen there. So that one is slide 3, I think. So this is the title of the slide, Quantum Critical Dynamics in a 5,000 qubit programmable Spinglass. It's a scientific paper, so this is really addressing core experts in this space. It's written in Nature, so if you see a lot of technical terms, that's the reason why, because it really connects to the physical systems that are sort of explaining why the dynamics of the system are faster. So why are dynamics important? So in optimization, dynamics mean your ability to move between solutions, the speed with which you can change the state as you're exploring one solution to the next. And as I sort of mentioned, all classical algorithms are running on the same hardware. So when I'm meeting with people who build industrial optimization solvers, there are literally like hundreds of algorithms that they could be building into that software. We run industrial optimization solvers, so we consider the same thing, but you can't maintain that much code all the time, right? You're trying to pick a smaller set that become a strong portfolio of optimization heuristics. And when you're building that portfolio, you want very strong contributors, but you want contributors that are diverse from one another, which means that they are strong when the others are weak and they catch each other's mistakes. And for that reason, you would always include quantum annealing because it's fundamentally different. All of the other algorithms have the same speed and the same dynamics. And quantum hardware is the only, quantum annealing hardware is the only technology that's been able to show that it has this increasing advantage relative to classical computers as the system grows in size. And as you can imagine, you're searching through a solution space, being able to move through the solution space more quickly is always going to be helpful to you.
Okay, question, are the only connectors available linked to Python libraries? What about C++?
Yeah, the Ocean software development kit is in Python. I mean, it has some elements in it which are written in C for speed. But they're always looking for issues and requests and things like that and add-ons. So if you want to, contribute that or work with a team, check out our GitHub page. I should almost switch screens again. Which is like our DWave Sys Ocean SDK, and then and ask the team questions and post issues and let's see what connections can be made to help you programming in C++.
Okay, we had a question regarding applications in production versus kind of research, and whether the applications that you went through today, whether any of them were in production.
Yeah, absolutely. So for instance, those Pattison Food Group applications, those are in production. They're running right now. They're running with these grocery delivery drivers and also in stores. I was actually recently on a trip to Japan, and NTT Docomo is running an application there in production where they're optimizing the paging signals between their base stations and cell phones. Particularly during peak periods, it reduces the amount of paging signals they need to run by 15%. Which effectively means a 15% increase in capacity for their network. So huge gains there. And so that application is running in production right now. A lot of our other customers working at application scale, they have done tests in production, they have run across real systems, or there might be in a process where they're preparing to go into their pilot production releases. So we're constantly working with customers, helping them through that journey. But yeah, there absolutely are commercial applications that are running with our quantum computing technology ongoing right now and for years. Okay,
we'll have time for just a few more. One question, most developers who start quantum computing and quantum machine learning start with IBM Qiskit. How can they transition to DWave? Also, can DWave Stack be used for quantum machine learning?
Yes. So if you are okay, so if you're using Qiskit, you're using a software development kit that's largely focused on gate model quantum programming. And so that means you're actually working down at the level of like constructing gates, which are actually just physical Hamiltonians that are interactions between the qubits. In a gate model system, you've got local interactions, and then you're creating a sequence of them over time. And in an annealing quantum computer, you have one large Hamiltonian that you're constructing, and it's applying across all the qubits for the entire computation. So that's kind of the key difference in the programming models. I think that a lot of, if I was going to try to sum it up, Qiskit is sort of teaching you quantum physics, right? It's helping you become a quantum physicist and understand the low-level algorithms. Whereas the Ocean software development kit, you don't need to know quantum physics to program an annealing system. You can focus on, the functional programming of capturing and expressing the problem that you're working on. So the two programming models are very different that way. And I think if you have a look at the programming resources or check out our programming core course or our quick start course, you may actually find it a little bit easier, but it's not like going to be a one-to-one because, Qiskit is trying to teach you quantum physics, whereas we're trying to teach you how to map applications to the system quickly and effectively. Both of them are useful tools for different audiences and different purposes. But I think a lot of developers we talk with find that they're able to pick up the Ocean SDK pretty quickly and get productive quite quickly. I mean, in some cases with engineers I've worked with, it's as fast as a week.
Okay, we'll do one more question, and then for all the questions we didn't get to, we will try and answer them via email. Also, we had a number of questions about the recording and the slides. So this is being recorded. It'll be posted to the DWave YouTube channel soon after the webinar. And we will send an email out to everyone who registered with information with a link to the recording and a link to the slides. So last question here, can we solve any mathematical model efficiently with this tool? I saw in some papers that it is efficient for some specific constraint sets, excuse me, like set covering constraints.
Okay, great question. So first, I'll mention that that web application resource where we talk about, we're looking at optimization problems where decisions are being made or not made. maybe they're in an integer class or in a category class, and the decisions that get made have a knock-on effect to the rest of the pool of resources in the network. So those are strong examples. I should mention that, while a class of problems is difficult, it's the actual instances themselves that determine the difficulty of a problem. So a good example of that would be factoring. Factoring semi-primes is known to be very difficult, and it's the foundation of RSA security encryption. But factoring itself, if you were just to take random problems, you'd run into a whole bunch of easy instances. Factoring 15 into 3 and 5 is like really trivially easy, and most problems are divisible by 5 numbers, right? 2, 3, 5, 7, and 11. So you could create a constant time algorithm, which is very effective at factoring numbers if you were just, factoring randomly selected problems. So quantum computers are really the backstop for those very, very difficult instances. And that's why we're using a combination of quantum and classical systems together. So yes, it is the case that, if you're factoring 15, you want to use a classical heuristic to do that and knock it out really quickly. And then if you run across a large semi-prime, you want to be able to backstop that with, a quantum computer in a hybrid fashion, so that will help you search through that difficult space. And businesses who are facing the kind of optimization challenges that we highlighted through the webinar, that's exactly the difficulty. They're in operating conditions that are changing every day. They're not studying the complexity of the problems as they're coming up. They just need effective solutions in the time that they have available to solve it. And they're finding regularly that they're able to use this the Leap Quantum Cloud platform and our quantum classical hybrid solvers to be able to bring them that value. So yeah, good intuition and a good sense, and explore this and work on some of these problems, and you'll really get a bit of a sense of what makes optimization problems difficult, and where this technology can provide value. And absolutely engage with our teams and talk with our launch teams, so that they can help you along that journey and help you quickly identify places in your business where you can get wins. Because in a business, if you can start producing a return on investment in an application that can be quickly deployed in a matter of months, then that's going to give you the foundation that you can start building off of to start looking for more applications in your business where you can create value. And it is absolutely the case that you can build value quickly with quantum computing today in quantum optimization.
Great. Well, thank you so much. And again, we'll send out these slides so you'll have access to all these links. But if you look at the DWave YouTube channel, go to the DWave website, go to Leap, you'll find a ton of information there. So thank you everyone so much for attending. We'll be sending out information about our next webinar soon. And thank you, Murray, for what's always a great talk. Thank you. Goodbye, everybody.
Thanks, Susan. Bye, everyone.